Alright, so here we are. So we're outside like the main library area, and we're on a little site visit. Okay, so you got pen and paper, but as you can see, we've got some columns, right? And then we've got some beams, right, that are bearing on top of it. Kind of got the primary beams running that way, forming this frame, and then you've got the secondary beams on top too. But then how this will tie into the last topic of this term, which is beam columns, is because beam columns is very much like a holistic kind of topic, right? So you kind of have to understand how the entire structure works, because beam columns is, the first thing you have to understand about it is it's to do with whether you've got a braced structure or if you've got a sway structure. Alright, firstly, I'll get you to start sketching stuff, and then as you're sketching stuff, you're going to have questions, right? And I'm going to try to answer those questions, right? So, alright, hello everyone. So you may have seen briefly the clip at the start. We did like a little site walk out to this area at UNSW, so you may or may not recognize it. It's near the post office, kind of around like the main library. And there's this kind of steel structure that's up at the moment. I think it might be temporary. I'm actually not sure what the purpose is, but the video cut out because the person filming it ran out of storage space, and also my microphone unplugged, and the video was a complete mess. But I'll just run through with you the intention and like the vibe of what I was trying to get across. So as you can see here, we've got a couple of steel frames, and it's good to kind of get an understanding of how these steel structures look in 3D, because in a lot of your courses at uni, including this one, you're thinking about these steel frames as if they're, you know, like 2D frames. But in reality, we know that, you know, every building pretty much ever is 3D, right? It needs to like encapsulate a space that people can occupy or whatever, right? So it's good to see how these steel frames kind of sit in alignment with each other, and how the whole structure gets tied together. Okay, so from what you can see here, essentially, right, we've got, I wonder if it's better if I give this a bit of opacity. It's not really, maybe I'll do that. Okay, so this will help show the lines better of what I'm trying to draw. But we've got a steel frame, right? I'll just highlight the closest one, right? So that's the that's the beam. This is a column. This is a column. Okay, and you can actually see some bracing as well. This is part of the bracing system too. So in white, what you can see up the top, I might do some different color. In white up here, you've got some kind of beam. Okay, so the first thing I was trying to get the students to do is identify the size of the beams, right? Because when you're physically standing there, right, and you don't have a measuring tape, you can still use your judgment on like how big these things are, right? So, you know, like, you know how long a 30 centimeter ruler is, right? So that's 300 mil. So it's like, you know, how big are these columns, right? We figured out these columns might be 250 UCs, okay? And if you're standing here, so we were standing around here and we were looking up, it's like, how big are the white beams, right? Like these primary beams. And you can see compared to the column size, right? You can probably guess these were about, I forgot what we landed on. I think 530 UB, right? Yeah, anyway, so you can kind of do like comparison like that. And then it's like, okay, what about these secondary beams up the top here? What are these? I think we might have ended up saying something like 310 UB. I can't quite remember what we decided on, but anyway, you might need to go on site one day if you're a structural engineer, and it might be an existing site and you might need to do some like retrofitting to it or whatever. Sometimes you need to just use your engineering judgment when you don't have all access to the drawings and stuff like that to figure out this kind of stuff, right? Anyway, so we're looking at this this kind of framing system, and it puts into perspective, I guess, one of the things is going back to like flexural design and the beams and stuff like that, right? How do I say this? Okay, so let's say these columns, right, act as a support for the beams. Okay, so this is like a continuous beam basically, right? The primary beam that we're looking at. All of these secondary beams actually act as point loads, okay? So I'm drawing an arrow for each of the the secondary beams, because they're supported by the weight of the beam as well as the column. Okay, so in reality, you know, you might have some kind of like free body diagram that looks like this when you're trying to model the primary beam. Okay, someone asked, at what point are these point loads that are next to each other considered UDLs? And it was a good question. I think they were spaced a bit too far away from each other, where I wouldn't really consider them uniform loads, but you could do it as a uniform load. I think if the spacing is close enough, you might want to just... Oh, sorry. If the spacing is close enough, you could do it as a UDL. Another thing is the idea of like flexural restraints, right? So if you think about the bending moment diagram, okay, actually, just for the sake of simplicity, let's pretend that a whole thing was a UDL, right? So all of these secondary beams, the bending moment diagram, because I don't want to draw it as point loads, might look something like this. Point loads would just be the same thing, but like more discrete, so kind of like that. But I've just smoothed it out, pretending that's like UDLs. Okay, so the bending moment diagram looks something like this, right? And because we've put the bending moment on the bottom side where it's got positive bending, this is an indication of what the tension flange will be. And so the opposite side, the compression flange, is our critical flange whenever we've got beams that are supported on both sides, so not cantilevers. So we know that the compression flange from like here to here and here to here and here to here is going to be our critical flange, right? And so therefore, these secondary beams actually serve another purpose. They're laterally restraining our beam. Okay, so they act as lateral restraints where there's positive bending on the top side, right? So that's in the gravity case load. If this whole building was like, sorry, if there wasn't holes everywhere, right? So there's sheeting on like all these walls and stuff like that, right? And say there's like a hole in this building, like a door or something, I don't know. Strong gust of wind blows in, okay? What happens is the pressure inside the building increases and it like puffs up like a balloon. And all the surfaces from the inside want to expand out, including the top surface, right? And then in that case, this beam experiences uplift, okay? And then your bending moment diagram, right, when you factor in the dead load and stuff like that as well, might look something like that instead. Okay, so we've got the opposite bending moment. And you have to think about, you know, critical flange restraints and stuff like that as well. So how's this beam being restrained on the bottom side? Okay, it's basically not, at least in this big span in the middle. What typically happens is you see these things if you've looked up in a warehouse, right? So say you go like bouldering or something, right? You might have seen these little diagonal thingies, struts, I guess you can call them. Braces, I guess, is even a better word. It's called fly bracing. So fly bracing, usually it's on both sides, so it'd be on the other side of this beam too. Yeah. Fly bracing is used to restrain the bottom flange of your beam. So it's got a flexural restraint as well. Okay. So anyway, yeah. So that's that. That's the beam. So this week's focusing on the column specifically, right? So what happens is this column, and this is this is basically a one-story structure, right? There's only the roof and the ground, but the topic that we're looking at considers like multiple floors and stuff like that. Anyway, so when there's multiple floors, you'll experience like a pretty big amount of load into going into your column, which will basically cause it to go into compression. We've kind of got a brace node here, and so if this wanted to buckle, it would have to do that. Okay. So it's not a complete like C shape or whatever. Anyway, so there's that, and also in the steel code, there's something called like the minimum moment as well. Okay, so it's something to do with like you take some eccentricity. I forgot the exact thing. I think it's either 100 mil or 200 mil, and you pretend that the point load's applied there, and then you figure out what moment. So if that point load going into columns again, it's like, okay, what happens if that point load's applied there? Hello, it's me in post-recording. So I found what I was fucking talking about. So in AS4100, talking about trusses and whatever, but then on this next page, a beam reaction or similar load on a column should be taken as as acting at a minimum distance of 100 mil. So I said 200, but I was wrong. At the face of a column towards the span or center of bearing, whichever gives the greatest eccentricity, except for column cap. The load shall then be taken as acting at the face of the column or the edge of packing if used towards the span. For a continuous column, bending moment should be taken as whatever. Okay, basically your loads on your beam and the travel into the column, right? And that's through a reaction, right? Okay, the idea is that beam reaction shall be taken as a minimum of 100 mil from the face of the column towards the span or the center of bearing. Right, whichever gives the greatest eccentricity. So you're doing that, okay, and then the distance you care about, the face of the column towards the span, so that has to be a minimum of 100 mil. Okay, so the reason that's important, right, is if your calculations say that there's no moment on your column, like that's not acceptable essentially. Your minimum moment has to be, P is like whatever reaction you have, right, multiplied by 0.1 meters, right, which is 100 mil, and that's your minimum moment, right? But in this course, I believe they'll just give you the moment in in the column. Anyway, so the point is, fuck, I'm all over the place. The point is, what we're checking this column for is the combination of axial load and bending moment, okay? And sometimes this bending moment, it's going the other way. Sometimes this bending moment can go biaxially as well. So bending like left-right here versus in and out of the page as well. So that's called biaxial bending, and this is called axial force and bending moment interaction, or compression and bending moment interaction. Anyway, so hopefully that just gives you some context of the structure. What I'm going to actually talk about today, yeah, the column thing. I'm going to start talking about the idea of second order effects, moment amplification. Essentially, these things are to do with sway versus brace structures. Okay, so that's kind of why I wanted to show you this example, right, which is like the entire context of structure, because it's very important to be able to identify the difference between a sway and a braced frame, because it will determine what type of moment amplification and like second order effects you're going to apply onto the structure, onto the columns, I guess, specifically. And then I'll go through like step by step of what you would do to design it, right? So, oh, and also, thank you very much, Prash. Those of you who don't know him, basically he was my tutor back in the day for steels, for concrete. He's just an excellent teacher, and I just copied his notes essentially for this week. All right. So, yeah, anyways, you've got the column, right? And let's just draw it up. You've got some kind of axial force, let's say N, and you've got some kind of bending moment acting on it, okay? And this is going to cause, so most columns in real life will basically experience these two things at once, right? And even if they're not, on paper, they're not experiencing the moment, it was that minimum moment thing that I was talking about from the steel code. Yeah, so there's two ways that moments will end up in columns, right, in real life. So the first one is through primary means, right? So if you imagine a frame and you've got a rigid moment connection, right? Essentially, your bending moment, right? Okay, let's ignore the lateral forces for a second, right? Your bending moment diagram looks something like this. Okay. So we've already got some kind of moment here at the top and the bottom, if it's rigidly connected, of your column. So that's one way that moment can get in, right? Just through like the normal force analysis that you would do. The other way is through second order effects, okay? And second order effects are due to eccentricity, okay? So the idea is that depending on if you've got a braced or a sway frame, all right? So the first one here is a sway frame, and the second one here is a brace frame. I haven't really drawn it, but the reason why this would be braced is there would be cross bracing or something, for example. Okay, So in the first case, the sway structure, right? Imagine my hands, right? The columns are here and here, and this is the beam. A sway frame, when it experiences, say, like a sideways wind load, will basically get hit and it will sway like this, okay? A brace frame, so if you imagine like, I don't know, strings or whatever tying my hands together, it would basically be able to resist the sideways load through the bracing system going into tension, and you basically, yeah, it's braced, it's not going to sway around and stuff like that, right? So, yeah, but instead of a sideways load, right, hitting like wind, what can happen as well is basically if there's a point load, okay, let me draw this out. So let's just consider a column and just pretend it's like a cantilever, like from the ground going upwards, okay? So if the load was applied directly, okay, my pen, right, is the column. If the load was applied directly on it with no offset in the load, you basically don't get any swaying, right, assuming the member doesn't buckle. But in reality, you have to account for something called like eccentric loading, and that's if my finger, the point load, is applied off to the side, okay? And if it's applied here, it's basically going to cause this to bend, okay? Bend over to the side. So, drawing that, pretend that this is connected to the beam and stuff like that. Basically, this would want to tip over like that, okay? For a sway frame, it would look like that. For a brace frame, right, during the same scenario, with the point load, it would instead do that, okay? When it's pushed down on, and basically the idea is that delta is the amount that it like sways off to the side, okay? And then here we've got big delta, right? So big delta is for like essentially sway frames or like cantilever cases, and small delta is for when you have braced cases. So like this one, like the top of the column can't move and the bottom of the column can't move, but the middle can move because it's not like restricted from moving there. And if you imagine like a ruler doing that, for example, right? You can imagine that the axial forces would like compound, because if this is like your ruler shape, for example, right, and you're pushing down on it, you can imagine like, and the ruler's like buckling basically, you can imagine that like, since the force isn't directly like traveling vertically downwards, right, you've got some kind of like bending moment that's induced, right, through this axial compression. So you have to account for that, okay? So the way that we account for this, right, so just recapping from what I said a little earlier, the primary means are from the actual forces itself, so this is your bending moment diagram stuff. The secondary moments are induced through like that eccentricity or the offset, and it's different depending on if you've got like a sway versus a brace frame. So these are due to P delta effects basically, right? So P standing for like a point load or an axial force, and then delta being how much it like is offset or moves, right? Anyway, so the way this manifests in the Australian Steel Code is, instead of adding these moments together, right, because from like a first principles point of view, it's added together, what we do is we get whatever bending moment we have, like that we can just work out through statics. But then instead of adding on the P delta effects, we multiply it by something called the moment amplification factor. So this is denoted by delta S or delta B. So this isn't like physically how much it moves. This is an amplification factor, okay? All right, so basically you've got a brace structure, right? And if there's no compression on it, so there's a column, right, in a brace structure. So put bracing like that. If there's no compression, then we don't have any moment amplification, right? So I don't even know what to draw here for you. Let's say like wind load, I don't know. Anyway, so this column's not experiencing like compression, then you don't have to amplify it, right? But if there is compression, let's say a point load which travels into your column as a reaction, if that's the case, then you basically have to amplify your moment. in that column. And the way that you do that, okay, this is the overall formula to calculate it, but it goes in steps, right? So the first thing you have to do is you have to find beta m, okay? So it's step 1, right? Step 1 goes into step 2, which is to find cm, which is your factor for unequal moments, and then step 2 goes into step 3, okay, because you substitute it in here, right? And this one's substituted in here, and then step 4 is you compute the amplified moment, okay? And this red one goes, sorry, that goes into here. Okay, so let's go to step 1. So for step 1, you're basically taking the ratio of the smaller moment to the larger moment, okay? The smaller to larger moment, and you've got this negative factor at the front. These are the bending moments at the ends of the column, right? So I'll give you an example. I'll give you several examples here, right? So this is from the same frame, and we've just mapped the bending moment onto it, but let's go to this top left one. Okay. So the smaller moment's 45, and the bigger moment's 50, right? But you have to remember that the bending moments are actually of opposite signs. So if they're the same sign, so for example, your bending moment looks like that, right? If you, let's go like that. Okay, so let's say that's 40, and that's 50, okay? Then beta m is negative 40 on 50, okay? For example. But since we have opposite signs, right? So we've got 45 going into 50, right? We have to go negative negative. Since they're different signs, then the beta m value ends up as positive, whereas this one would have been negative, okay? So yeah, I've just got some examples for you. If we've got like a pin base, for example, it ends up having like 0 moment on one of the ratios. You'll have 0 moment on the smaller side, and therefore beta m ends up being 0. Okay, so that's how you find beta m. So now using beta m, we chuck it into this formula, okay, and this number has to stay less than 1, and the reason that's important is because beta m can be negative sometimes. So in this case, for example, yeah, just keep cm under 1. Cm goes into delta b, the b standing for braced, okay, so remember this for the brace case. And then n is from our axial force diagram, or axial force analysis, okay. And then I'll tell you about another step, okay. So this is step 2.5, I guess, okay. So 2.5 is finding norm, okay. So yeah, norm is the reference buckling, not moment, what's the word I'm looking for? Reference buckling load, okay, from Euler's equation, and it follows this formula, and basically KE, you have to find through gamma method, okay, so if this was step 2.5, this is step 2.75, okay, and then this can take a while depending on whether you're using gamma method or not. I'll talk about that a bit later. It's in my notes below, okay. But anyway, and then you compute step 3, and then you get step 4, okay. So that's an amplified moment. For sway structures, okay, what you do is basically you figure out. Let's call this step. Yeah, it's called step 1 and step 2 for all of the columns in a story. So if we've got 4 columns, for example, in a story, like this, you have to compute the reference buckling load and the axial load in each of these columns, right? 4 times, okay? And then step 3 is you chuck these into this equation, okay? And then it's the sum of them, so it'd be like whatever plus whatever plus whatever over whatever plus whatever plus whatever, okay? And that's how you find lambda ms. So lambda ms is the elastic buckling load factor for the entire story, and using that you chuck it into step 4, which is your moment amp factor for sway structures, okay? And then you chuck into step 5. Alright, So, yeah, the reason why this can get annoying, so let's call this one step 1.5 here. Okay, so either step 2.75 or 1.5, you have to look at the gamma method again. Okay, so I'll show you gamma method again. So that's from week 3. I didn't talk about it in this series, but some people were looking at my old Steelfixer's Guide to the Galaxy from last year, where I was talking about it in week 3. So there is already a video like covering it, but you don't need it until this week, where you can be tested on gamma method. So gamma method feeds into the beam column design essentially, right? Okay, so let's see the step-by-step of what you got to do, okay? So step 1 is basically find the bending moments and axial forces, okay? Sometimes it's given to you already. Okay, step 2, oh, that should be S there, anyway. Yeah, you basically have to find these factors, the moment amp factors, and then this may or may not involve gamma method, okay? The reason I say it may or may not involve gamma method is it used to definitely involve gamma method when Hamid ran this course, and when Mark Bradford ran this course, but now I'm not sure if Brian tests this, right? I don't think it's actually, I actually haven't seen it tested, to be honest, but I'm going to show you it anyway because I never say that something's 100% not going to be tested when I'm not sure, okay? Okay, and then you do compression design, so this is from week 2. The reason you do compression design is we're doing a column, right? So if this is a column, let's say it's like an I column, you have to figure out whether this is going to fail under, you have to find the section capacity, you have to find the, what's it called? Member capacity, right? Of this column in compression, and then also do it for flexure. Okay, so this column, because under it's experiencing like a bending moment as well. You have to basically do the max moment multiplied by whatever moment amp factor that you got from the first step. Okay, so that's how you do flexural design. And then there's also combined checks to check axial forces on top of your bending moments, right? Because sometimes they can interact and reduce their like capacities with each other, right? Okay. So step by step, yep, apply wind, oh sorry, not wind load, apply the load combinations, get the bending moment diagrams, axial force diagrams. Sorry, you don't really need shear force diagrams. The only reason you might want a shear force diagram is to end up getting the bending moment diagram. So these ones are the important ones. Sometimes, for example, so let's say this is a beam, right? But this also applies to columns, right? If you've got like vertical loading on a beam, you basically get this one. So you would have bending in the XX direction, but also if you have wind loading, for example, right, off to the side of this beam, your bending moment actually, like the beam wants to go sideways, right? So the bending moment diagram, you would actually map sideways, and that would be MY. So the reason it's MY is because it's bending about the YY axis, okay? Here's an example of how you would do a load rundown basically to find the column, sorry, the axial force in the column. So say you were designing these bottom 2 columns, right? Then you would basically take the loads and find however much load is going into each of these columns, and you can treat it like a simply supported beam. 50% of the load that it's taking on each floor ends up going down the column, and the reason for that, oh sorry, and then what I've done here in the calculations is I've called this the trib width. So the idea of a trib width is basically essentially how much of the length, oh sorry, I guess this is a trib length, but anyway, I think it's called trib width anyway. So trib width is basically how much of the beam's length is going into the column as a percentage of the forces it's taking, right? So for uniformly distributed loads on simply supported beams like this, you'd basically treat it like 50-50 going into each one. So if this length was 6 meters, then there's 3 meters of load going to the left and 3 meters of load going to the right. And you do that and you add it up onto each column. The way that I've been explaining this to my first and second year students is, imagine a bunch of columns. It has like a stack of children, okay, and they're all giving each other like piggyback rides, right? The dude at the top, he only has to account for his own self-weight. The guy underneath has to carry the dude on top self-weight and his own self-weight, and the guy at the bottom carries all three of their self-weights, right? So the reason this is important for columns is because each level of the column has to basically carry the load of the columns above it, right? So at the very bottom, you have the most amount of axial compression because you're gonna have all the loads from the previous floors like stacked up and added on, okay? And that's basically the way that like loads flow into the ground, because the idea is that loads want to travel and dissipate, right? It's not too different from, say, like electricity, right? It wants to find like a path to complete the circuit or whatever, and so forces want to find their way into the ground and dissipate, okay? Alright, so next thing you gotta do is you have to find all these values from one steel, right? So this is for non-custom sections, and the reason for this is all preparation for gamma method. I mean, not all of it is preparation for gamma method, but what you can see here, the majority of these values are for gamma method, but some of them will be for the compression and flexural design. Okay, yeah, so here's how we use gamma method basically in order to find effective length factor, okay? So if you remember from the second week in compression, what I've basically got up to is there was like this table, okay, and I'll just roughly draw it out. It'll be something like, here's the KE value for various cases, okay, and then it would be like, these ones were like sway, and these ones were like brace, or maybe it was the other way around. This one was braced, this one was sway, right, and there's like different cases that they give you and whatever. Yeah, and then so one scenario might be it's braced and it's like pin. One would be one side is pinned and the other is like rigid. Another one would be like, you know, it's rigid, and then there'd be different ones for sway or whatever as well. And the idea is that, you know, I don't remember exactly what this table looks like, right? But there would be like a factor of KE of like 1 for this one. Pin. There'd be a factor of like 0.7 and 0.5 or whatever. And the idea is that you're thinking about the length of the C shape that is caused when we put this into compression, essentially. So these are your effective length factors, right? And the reason is, if this is pinned and the bottom is rigid, the bottom being rigid wants to basically keep this part touching the rigid connection at like a 90-degree angle. Right, and then same with here and here, so this has to be 90 degrees, this has to be 90 degrees, and so therefore the buckled shape has to basically follow that kind of line. And that 0.7 factor comes from, you know, the length, the effective length of this, right? So if this whole thing is L, right, you basically multiply what L by 70% for that second case, and then like 50% for this third case, etc. Pin is like 100%. Anyway, so that's like the simple method, right? So this is the simplified method. Now with gamma method, like you're basically trying to, effectively this is to do with rotational stiffness. Okay, so stiffness. So the idea is how much are these joints actually rotating in real life, and therefore how long will the effective length be? Okay, that's what this comes down to, and you can actually calculate this very accurately depending on the exact size of the beams and the columns and stuff like that that are connected to your node that you're analyzing, and so yeah, the gamma method like is the most accurate calculation for this essentially, right? Okay. So if you've got a column and it looks like this, okay, you've got the top and the bottom, right? So here's top, here's bottom. Gamma, it's called the gamma method because you're finding this like gamma value, right, which is just like some constant. So you're trying to find what is the rotational stiffness at the top and what is the rotational stiffness at the bottom. So the rotational stiffness is indicated by some number, gamma t for the top and then gamma b for the bottom, okay? So basically, yeah, like the general formula follows this, okay? So if how to say this? Okay, let's say you've got a multi-story building that looks like that, okay? So it looks like that. It depends which column you're looking at. Let's say we're looking at the middle floor, okay? Or like a column that's sitting on the middle floor. Floor 1, okay? So basically, like if we're analyzing this column, we've got the top here and the bottom here, right? The idea is that you basically use this formula and you'd have to use it twice, one for the top here and one for the bottom here, right? So you apply it twice. But if instead we're analyzing this column here, okay? So this is top, this is bottom. The idea is that the bottom, it can only be one of two numbers, okay? And the reason for that is if you've got a column to footing joint, so a footing is basically where the column touches the ground, right? So we're analyzing a ground floor column, right? If we have a rigid connection or if we have a pin connection, it can be one or the other, okay? So if it's a rigid connection, gamma bottom is 0.6, whereas if it's pinned, gamma bottom is 10. So basically the idea is that whenever you have a gamma value that's lower equals stiffer, yeah, and then whenever you have a value that's higher is looser, I guess you can say, okay? Anyway, so I'll show you how this ends up manifesting, but basically you, like on the top of the fraction, you want to sum all of the inertia values for the columns over the column's lengths, and these are the columns that are touching it, okay? So what I mean by that is if we were looking at this first column, for example, again, right? You want to basically find the properties of the columns above, oh, so sorry, okay, my bad. Okay. Let's say we're looking at this node, okay? We're analyzing this node, let's say we're analyzing gamma top. The sum of the columns means the column above it and the column that we're analyzing itself, okay? So it's to do with the connectivity to the node, okay? And then basically, I'm running out of colors. Let's go green, okay? So for the beams, right? The beams are, what are the beams that are touching that node as well, okay? Yeah, and then beta E is, so beta E can be something from this table, or if the near end of the beam is pinned, it's overridden as 0, okay? So what I mean by that is, what I mean by that is if you have a pinned connection to that beam, beta E ends up being 0, and therefore you don't need to calculate this, right? So if this is 0 at the bottom of the fraction, for example, and it's only touching one beam, gamma T ends up being infinity, right? Because when you divide by 0, you go to infinity. And anyway, so you find those values. Here's an example of, say we're looking at this node here. So we're trying to work out, let's say, gamma T, all right, which is that upper node. We're doing the sum of the stuff at the top being the columns, right? So let's call that column 1, this one column 2, right? You would do all that stuff related to column 1 plus all that stuff related to column 2, and you're summing it over beta E of the stuff to do with beam 1. Let's say this one's B1. Let's say this one is B2. Okay. So BE. So this can be a different BE value, right? By the way. And that's B2. Okay. So the idea is that B1 is pinned. The near end of the beam is pinned, and so this ends up being 0, and so therefore we don't need to calculate that stuff. But this one we'll need to calculate, and then BE, the far end of the beam is rigid, and so we look at this table, for example, let's just say it was part of a brace system, like that. Okay, the far end of the beam is, did I say rigid? Yeah, let's say it's rigid. Therefore it would be 1, okay, for example. So that would be 1, okay? And then you compute all the stuff, and all the stuff in the brackets are like either like physical dimensions of the beams or cross-sectional properties. Yeah. Okay. Yep. Okay, so what do you do with this information? Basically, this is a symmetrical, like diagonally symmetrical graph, right? And there's 2 of them. Okay, so this first one that I've shown you is for braced members, and this bottom one is for sway members. Okay, so the idea is first you have to figure out whether your column's going to do this or this, right? So if it does the thing on the left, it's braced, right? So if it's got cross bracing, for example, it's braced. Otherwise, if it's sway, you know. So the idea is KE can be, like, it has to be less than or equal to 1 for a base member, okay? But for a sway member, it's greater than or equal to 1, okay? So, yeah, you're going to get these 2 values for the top and the bottom. Let's say the top you end up getting, I don't know, 3, okay? And then the bottom you end up getting 2. All right, you find this value here, you draw a line that interpolates the data. Let's say it's 0.875 or whatever, for example. So now you have this, so yeah, that would be like gamma. So it actually doesn't matter which side you take it because it's symmetrical. So let's say that it was gamma t, that one was gamma b, but you can go the other way around as well. You get the same number. This is your KE value, right? And that's what you end up multiplying to the length to get the effective length, okay? All right, and you have to figure it out in both directions as well. So whether your column, so looking top down at the column, whether your column is bending that way, so that would be the YY direction. Yeah, so it's bending left and right based on what you can see, or up and down based on what you can see. It'll be a different value for KE and KY, okay? So you have to figure out the stiffness, the rotational stiffness 2 ways, and you have to figure out the braced length 2 ways as well, okay? So just put on your like thinking cap for compression again, right? We're thinking about compression effective lengths here, okay? All right, taking off your compression thinking cap, right? And then putting on your, I mean this is to do with compression too, technically, right? Anyway, whatever. So this is just my notes from earlier, the ones that you've already seen, but I've just put it a part of like the step-by-step. Okay, so yep, these were the moment amp factors, right? Yeah, you figure out that stuff. We're still thinking about compression. Sorry, I didn't mean to say we were thinking about moment yet. We're still thinking about compression. We're trying to figure out, like, we found these values through gamma method. Okay, we're trying to figure out the max slenderness, whether it's going to buckle in the x direction or y direction. Okay, and then axial capacity, so still thinking about weak 2 compression, all that stuff, still thinking about weak 2 compression. Still thinking about weak 2 compression, we want to find alpha C. Alpha C is what we multiply by the section capacity in compression, and that's how we get the member capacity, right? And then do these checks to make sure it's finding compression by itself. Okay, and then now we're putting on our flexural capacity cap, okay, and we're finding the nominal section bending capacity. So remember, you have to multiply for the moment amp, right? So whatever bending moment that you got, you multiply by whatever value you got in the moment amplification step, okay? Check if the member has full lateral restraint. In other words, is there a risk of lateral torsional buckling? Okay, and then if so, we have to find the lateral torsional buckling capacity. Okay, so the member's capacity, right? And yeah, so we basically have to figure out a different effective length factor. So this is different to the compression one, right? The compression one's the one that you apply gamma method for. The flexural one, you apply all these K factors that aren't the KE factor. Alright, so you had to apply the twist restraint factor, load height factor, the lateral rotational restraint factor, right? So that's all from flexure, that's all from flexure. You find your reference buckling moment, and then you get alpha S. Alpha S is your slenderness reduction factor in flexure, okay? And the moment mod factor, again, is to do with the bending moment diagram. Okay, so this is all for flexure. Okay, and yep, okay. Okay, so beta M here is a different beta M. Well, it's for the intermediate step in this table to find alpha M. Okay, so there's a different beta M to the one you just saw earlier. Was it beta M? I know there's beta E. Oh yeah, there's a different beta M. Okay, there's a different beta M for moment M. Okay, yeah, member buckling capacity. Okay, basically we're just checking that the member's not going to break in the amplified bending moment, okay? Alright, so here's where there's new stuff. We basically have to reduce the section capacity due to combined action sometimes. Okay, so we've basically at this point, we've figured out what M is, right? M is whatever bending moment that you got multiplied by the moment amp factor. And we've figured out the axial force through load rundown. Or maybe it's given sometimes. We figured out what section capacity you've got, for example, right? And we figured out, yeah, so we figured out the flexural section capacity and the axial force capacity, axial compression capacity. So now we can use that information and find the reduced section capacity. So it just comes down to that value that we're looking for in red is equal to this in purple, okay? And you do that for both directions, okay? Okay, and then combined member checks. So this is biaxial bending. So before was accounting for if you've got axial load on your column and a moment. Here we're checking for biaxial bending, which is bending moment in the x direction and the bending moment in the y direction too. Yeah, and then it comes down to these formulas, right? Okay, so you follow this flow chart, right? You check if you've got in plane. You check. Okay, you check does the member bend about the x-axis or not, right? And if yes, sorry, if no, you do this formula. If yes, you do this formula. Then you check, is there sufficient restraint to prevent lateral torsion or buckling? If yes, you can skip this step. If not, you have to check the out of plane requirements too. And then, is the column under biaxial bending? If not, then you're done. If yes, you have to check for biaxial bending. So biaxial bending, follow these formulas, okay? So, yeah, there's just like tons of different shit to look at basically, and it's really easy to mix up the subscripts here. Actually, my camera is covering one of them. There you go. Okay, and yeah, so just be really careful when you're reading all these formulas, but this is a matter of plugging in formulas basically. But yeah, you just do questions and then you get used to it, alright? Okay, cool. So that's all there is, and thank you for joining me in this series, the 2026 Steelfixers Guide. I probably won't be recording another Steelfixers Guide next year. So yeah, this should be the legacy that's left behind. I will be recording a little recap workshop that SevSoc's hosting. So that'll be happening on Monday. And I'm not sure when the video will come out, but soon after that. I'll be going through a past paper with another PhD student there too. Okay, so yeah, hope you can join us for that, and otherwise, thank you for watching.